Okay, so we're going to be analyzing capacitors today. It's going to be what chapter 16 is about as well. And what a capacitor physically is, well, we've been looking at what a single electron or a single proton does by itself is these two objects by themselves, left alone, send out electric field uniformly in all directions. So with these particles by themselves, it's actually very hard to try to get a series to create an electric field where all the lines go in the same direction. Because here in the middle between these two particles, as long as you have a proton and an electron, the field will continue from one side to the other. But any other spot near these things, the field lines are going to bend and warp or shoot off into the universe, not pointing in a straight path from point A to point B, not all going in the same direction. This is where a capacitor comes in. The idea of a capacitor is instead of having single particles some distance from one another, you have two parallel objects, one of which has a positive charge all the way across it, one of which has a negative charge all the way across it. And the effect that this has is the space between those two objects has a uniform electric field inside of it, where all the lines are parallel and pointing in the same direction. This is very useful because it gives us more control over what's happening inside of the capacitor, more control than we have if we just have two particles and we just start throwing other particles at them. We have a nice uniform and controlled space in there. And this can pave the way for some interesting things. One thing specifically that this helped with was older televisions. Because old TVs, tube TVs, the ones that had like the big old piece on the back there that just made them the worst thing to carry.
Yes.
So you guys have seen some of those?
Yeah, very
We
good.
still have one.
Okay, they
Those
still exist. Cool. My entire childhood was figuring out how to connect all of my VCRs and game consoles to these things. And all of this space back here is basically made up of vacuum tubes that have a very similar principle in them. The goal is to create a uniform electric field that fires electrons in a straight line in the same direction every single time. And those electrons hitting the pixels of the screen is what made it work. So, very useful thing in electronics and in circuitry. A lot of what we have today wouldn't exist without capacitors. And the capacitor itself is just a contained uniform electric field. There is an E field in here that, again, the goal is to have everything pointing in the same direction. These devices are useful, A, for TVs, B, they're kind of the first thing similar to a battery that was ever invented. Because you can store a bunch of electrons in that field. When you have a capacitor in a circuit and flip the switch, there's now an electric field in the capacitor, and electrons will naturally just sort of isolate themselves in here until they're all able to get out at once. They'll just exist in the electric field. So it can store charge and store electricity in it. And that's one of the things we're going to be looking at today as we actually put some physical capacitors into some circuits. Now, that drawing is not what a capacitor would look like if you had managed to buy one from Radio Shack before they closed down. Of all the things on the table, these things are the actual capacitors for today. It kind of just looks like a piece of candy with two pieces of metal sticking out of either side. This is these two metal plates. Imagine two big sheets of aluminum a small distance apart and then someone just rolled it up into a can shape. So this whole flat set of aluminum sheets has just been compressed and rolled into this tube right here.
But they're not touching each other?
They are not touching each other. To have a capacitor, these two plates have to be some distance apart. If they were just touching with nothing between them, then electricity would just flow and you'd just have a circuit instead of a capacitor. So yes, the two sheets, even though they're all rolled up in this can, still can't touch each other. And we are going to look at A, what these do in circuits, how they interact with the circuit and with each other, and B, how to make one. We're actually going to make some pie pan capacitors. So, step one. Let's look at the capacitor math that we're going to actually need today. The first and main formula for a capacitor is C equals Q over V. It's the first formula for today. And this formula is the one that defines the capacitor itself. The C is a variable for capacitance. This is the actual measurement of how good a capacitor you have. The stronger the capacitor, the higher its capacitance. This is measured in a unit called farads, named after, I believe, a physicist named Faraday. Same guy who the Faraday cave is named after. So, the variable is capacitance. It is measured in farads. And every table has two capacitors on it. There's another pile of them here for you to manipulate later if you need to. The two sizes of capacitor you have are 330 microfarads and 100 microfarads. So they're very small. Most are about this size. Kind of like coulombs, you don't really need super big numbers. So this is the actual measurement of the capacitor's ability itself. The other numbers we have here are charge, still in coulombs. I apologize that Q's unit is C and capacitance is variable is C. The way that I remember it is, if it's a variable, it's the word capacitance. If it's a unit, it's the unit charge, coulombs, sorry. The last part of this formula is the voltage.
Is that a capital V?
Yes, it is.
I think we use the letter V in physics way too much, okay?
That's fair. That is fair, because velocity is a very common, I forgot how to speak, very common thing that is measured. But voltage and its unit of volts are capital V's. Velocity is lowercase v, if that helps.
Okay, then what's volume?
Also a capital V. The only real difference there is, are you looking at like physical metrics or are you looking at electricity? I don't think there would be a formula that would commonly have both in it. I would hope. For the sake of electrical formulas, capital V refers to voltage. And that's a word you've probably heard before. I've tried to mention once or twice that the idea of voltage is kind of like the water pressure that is pushing the electricity along. For today's experiments, when we do have electricity hooked up and going, we're going to be using these D-cell 3 volt. Well, these are 1.5 volt, aren't they? Yes. So these are just normal off-the-shelf D cells, and these are each 1.5 volts. When we wire these up into a circuit, they are going to add up to 3 volts. And so that's going to be the total voltage driving any circuit we hook up today. So, for our capacitors, the capacitance of the capacitor is equal to the charge that is currently stored inside of it divided by the voltage that is currently being applied to it. So for, again, every circuit today, we're going to be using 3 volts. So there's always going to be a 3 down here. And every capacitor will have the written max capacitance on it. So the purpose of this formula today is going to be to try to figure out the maximum charge that the capacitors would be holding in this circuit. That is the purpose of this formula for today's exercises. And this, again, defines what the capacitor itself does and represents in the circuit. Our second set of formulas is what capacitors do in a circuit. And I want to show you quickly so that we can start building and hypothesizing about them. These are rough outlines of the 2 types of circuits that are commonly utilized. These circuit diagrams are going, these types of circuit diagrams are going to show up pretty often in these labs because we're going to be building circuits and what everything in these diagrams represents, because each of these symbols means something. These 2 parts that look like 2, these lines are parallel but not the same size, those represent where the battery goes. So every circuit should have either 2 sets of those lines or 1 set of those lines. As long as the lines aren't the same size, it represents the battery. Every circuit needs some power source. We're going to be using the batteries for that. The other symbol present in these diagrams is these 2 parallel lines that are the same size. And this symbol represents the capacitor itself. So wherever you see 2 parallel lines of the same size is where a capacitor goes. And to build a circuit, all you really need to do is find a marker with ink in it. Then you take your battery, connect wires to one end of it, connect those wires to one end of the capacitor, then connect the other end of the capacitor to the other end of the battery. And that's all you need to really build a whole circuit. This would be one circuit with, if we were using 2 batteries, it'd be 3 volts and 1 capacitor in it. And this would be connected and it would be doing its job. The total capacitance of the circuit would be the capacitance of the 1 capacitor. Total voltage would be total voltage of the batteries. And by itself, this would function, this would do whatever you needed to. You could put a light bulb in here instead and it would turn on and everything would be hunky-dory. But most circuits in electronics and in construction are not usually that simple. Usually a lot of things are wired in together, which is why we have these 2 different patterns for circuits. Has anyone actually dealt with these 2 different circuit types before? Okay. Couple of nodding. It's okay if you didn't, just wanted to see. For those who remember, do you remember the name for each of the types?
Series and parallel.
Very good. So this one on the left is called a series circuit. The one on the right is called a parallel circuit. These names come from the fact that on the left, the 2 capacitors, this is from the capacitor's perspective, these 2 things are in series with one another. They're wired one after the other. Any electricity that goes through the first one has to also go through the second one before going back to the battery and continuing. Parallel circuits are different because we have 2 different pathways that are literally parallel to one another. And electricity coming out of the battery can either go down this path or down this path, but not both in the same lap. So a series circuit directs all the current through everything. A parallel circuit will split it down different branches. And these create different totals for the capacitance of a circuit. What type of circuit you're dealing with will change how the capacitance is added together. And that's the first exercise for today, is looking at the circuits drawn on the picture, trying to figure out what their total capacitance is. The math for that, in a parallel circuit, the total capacitance is equal to the sum of every capacitor present. I'm going to label this as C1, this is C2. If you dealt with circuits before and you're remembering resistors in a circuit, this might seem backwards, because it is.
Because they were like fractions, right?
Right. If you've dealt with resistors in a circuit before, this is how resistors act in series, but capacitors act this way in parallel. So the more capacitors you wire in parallel, the more branches you add here, you drive up the total capacitance of the entire circuit. That whole circuit is able to store more electrons in it. This is different to if you were wiring a bunch of capacitors in series. So I'm going to label these as C1 and C2 as well. And this formula looks a little funny. 1 over C total is equal to 1 over C1 plus 1 over C2, so on and so forth for however many capacitors you have. Again, if you've dealt with resistors before, this is completely reversed. And that's okay. So in series, adding more capacitors will actually drive the total capacitance of the entire circuit down. The reason for that is if you add, because in this orientation, the current has to go through all of them. And when a capacitor is in a circuit, it takes a little bit of time for it to actually accumulate electrons in itself and for those electrons to cross from one side to the other and for the current to continue. The more capacitors in a line like that, the longer it takes for all of them to reach their full charge and to allow the current to continue. Excuse me. So, for the first part of the lab, we're going to be looking at the two types of circuits, figuring out how various combinations are going to add together. There's been a lot of preamble so far. You guys have any questions? Okay. I'm going to stop here. I'm going to ask you guys to go ahead and start looking at the first part, and I'll help you guys out as you are doing the calculating.